Okay, so now let's look at the notion of retractions on quotient manifolds. All right. So let's consider quotient manifold M, which is a quotient of a bigger manifold M bar by some sort of equivalence relationship. Okay. And then, of course, there's a natural projection map from M bar to M. This is the canonical projection. And if you endow this space with the notion of a horizontal sort of subspace or horizontal distribution, so if you're given a horizontal distribution, right, then there's the notion of a horizontal lift. Of a tangent vector say c in t pi x bar at the point to the manifold M, right, to what I'm going to call the c bar x bar, right, which is an element of t x bar m bar. Okay, so maybe it's a little bit easier. It's like to keep all of this in mind if we think about what our ultimate goal is. Our ultimate goal is that we would like to construct a retraction on this quotient manifold, right? And as you might expect, it's like the way you do this is to have a retraction. It's like on M bar with some invariance properties. Okay, so let's think about what that is. Okay, so if you have the tangent space to M bar mapped to M bar, this is of course where the retraction, it's like for M bar lives, right? So map from Tm bar to M. Okay, and then you have the projection from M bar to M, right? This is the canonical projection. And then there's the notion of the tangent lift of that map, right? Which induces then a map from Tm bar to Tm. And of course, Tm to M is where you would like the retraction you're trying to construct to live here. Okay. And while we're there, it's like there's this notion of a horizontal lift, right? So if you have something, some tangent vector here, you want to lift it to a tangent vector up here in some sense. Okay. So that's where everything lives. So let me sort of state the proposition, which then allows us to sort of induce a retraction, a well-defined retraction. It's like on M, it's like from a retraction on M bar. Okay, so let me state the proposition. So the proposition is that, so you have M is equal to M bar quotiented by an equivalence relationship via quotient manifold. And I'm going to endow this quotient manifold with a horizontal distribution, right? And if you recall, it's like, it's like one very obvious natural choice of a horizontal distribution. Let me sort of draw a picture for you. It's the following. All right. So if this is M bar, which is sort of the big space, and then this thing at the bottom is what I call M, right? Then there's the fiber. It's like, so given a point X on M, there's this fiber of points which are given by pi inverse of x, right? So these are the points, it's like which in M bar, which project to the same base point x, it's like in M. Okay, so so if you have some fiber like this, right, then what happens is that if you are at a point x bar here, right, which is an element, so x bar is an element of this fiber, okay, and you want to, if you will, if you want to decompose the tangent spaces into horizontal and vertical directions, then there's a very natural way to do this, okay? And the natural way to do this is to have the vertical spaces, it's like be associated to the tangent to this surface, right? So pi inverse x, right, is contained in M bar. So you can look at the tangent space to pi inverse of x, right? This gives you the vertical spaces. So this gives you the vertical space. Right, so let me sort of maybe do it here, right? So the vertical part is associated with t pi inverse, if you will, right? So there's this fiber, it's like in the tangents to these fibers, it's like give you a vertical space. And then if you want a horizontal space which is complementary to that, is, you know, it's like in the setting we're looking at, M bar is usually some sort of Riemannian manifold. There's a Riemannian structure there. And so once you've chosen the vertical space, you can look at the orthogonal complement with respect to the Riemannian inner product to then get the horizontal space. So we can choose a horizontal space that's just orthogonal to the vertical space, right? And that gives you this kind of prescribed horizontal distribution. Of course, you can construct the horizontal distribution in a variety of ways, but again, in a Riemannian setting, it's quite natural to have that the horizontal space be just the orthogonal complement with respect to the Riemannian inner product, okay? So anyway, so that's sort of the setting. It's like that's a brief reminder of where we're at. Okay, so you have M, it's like which is M bar, it's a quotient and equivalence relationship. This is a quotient manifold, and there's a prescribed horizontal distribution. Okay, and then we're going to endow, it's like M bar with a retraction, which we call R bar, which is a map from Tm bar to M with the rigidity condition, if you remember. Okay, so let R bar be a retraction on M bar with sort of a certain property, right? So whenever you have this kind of quotient manifold structure, the natural choice it's like you would want to make, right, obviously, is that if you want something from here to here, right, one sort of way to think about this is one thing you could certainly do is to have, if you want to define this R, one thing you can do is to start with a vector, it's like in Tm, right? You do the horizontal lift. This gives you a vector in, which is an element of Tm bar. You can apply the retraction, you get something in M bar, and then you can do the projection to get back to M, right? So you can do horizontal lift, retraction on M bar, and then do the projection to give you a candidate, it's like for a retraction map on M. Okay? So, and the point is that, you know, in order for this to make sense, right, there has to be some sort of invariance property, if you will, of R bar so that this is well defined, okay? So let's see how you go about doing that. So R bar is a retraction at M bar with the following property, so such that for all x on the manifold M and all tangent vectors, right, at this point, we have the property that if you look at the horizontal lift of this, there's an independence condition, so that there's an invariance property. Okay, so let me try to explain why you have to have a condition like this and what even it means, right? So the problem is that you're now starting, it's like here, it's like in TM. So there's a base point, it's like to that, it's like which I'm calling X, right? So there's this X here, and I want to, and if I have the distribution, there's a horizontal lift. So you might ask, it's like, where is the, why is there a need, it's like to require that this retraction, it's like be invariant in some appropriate sense. And the reason why it needs to be invariant is that when we talk about a horizontal lift, the horizontal lift is well defined. It's like once I've chosen the horizontal distribution, as long as I pick where X bar is, okay? So now, if I had a point X and I want to pick X bar, which is in the pre-image of the projection map, I have a lot of choices, right? Anything along this fiber is an acceptable X bar, okay? So if I pick X bar, there's a unique lift of the tangent vector, it's like at X, to C bar, and then I can do this construction, everything is well defined. But I had that initial flexibility to choose what X bar is, okay? And that's exactly what's happening here. Okay, so I'm saying that X bar A and X bar B are both things which are in the fiber. It's like over X, okay? And I want that when I take this horizontal lift, it's like to the tangent vector, it's like which is at the point X bar A, right? And do this construction, that if I had done the same thing and lifted it to a point X bar B, it's like the same, you get the same result at the level of this map. Okay, so that's really what this condition is saying. It's nothing mysterious, and it again just has to do with the fact that you know, the horizontal lift is well defined once you pick which point it's like in M bar, it's like which is in the fiber you want to work with, but you have the flexibility to choose what X bar is, and this is exactly the flexibility which I'm trying to check. That, you know, it's like going around this loop in this way is independent of that choice. Okay, so and this needs to be true for all. Let's see, for all X bar A and X bar B, which are in the fiber, pi inverse of X. Okay. All right, so if that's true, then this gives you a well-defined retraction. It's like on R. That's the main point, right? So then, okay, R X C, which is defined now to be pi of R bar X bar at C bar X bar, right, is a retraction. On M. So the bottom line is that this is something that's like one typically has to do again and again. It's like when you're trying to look at something which is defined, it's like on the full space, and then you have a space which is sort of a quotient of that, right, with some sort of equivalence relationship. You want to find, or you want to check that lifting from something in this quotient space to an element of the equivalence class, and then sort of inducing the map, it's like by then projecting it back, right, gives you something which is well defined, right? So, and so this condition here is exactly the condition that, you know, doing this horizontal lift, applying the retraction on M bar and then projecting back gives you a well-defined map. It's like from Tm to M, okay? So let me sort of just say a bit about the proof, but I mean, it's like, again, the essential idea is that, or I mean, the thing that's like to keep in mind is that this gives you a well-defined map. Okay. So the proof is that, so let's call that equation star, right? So equation star is just saying that this R is well-defined, so guarantees as a mapping from Tm to M, Okay. So since R bar is a retraction, it follows that Rx of 0x, right, is equal to x is satisfied. Okay. And then finally, the local rigidity condition holds, since if you have a point x bar in the fiber, right, then the linearization of this retraction, it's like here, okay, in a certain direction is equal to d pi x bar composed with the so I'm just basically applying the chain rule carefully. Okay. Erase the proposition. Right. So I mean, the way I do this, of course, is that I'm using this definition. It's like of the retraction. It's like in terms of the horizontal lift. It's like composed to the retraction, composed to the projection, right? Okay, and then then you apply. It's like the chain rule. It's like to that characterization of the retraction in terms of these composition of maps, and that's what you get. Okay, and then this is equal to d pi x bar acting in this direction, which is just the original thing, right? So this is just telling you that the linearization of the retraction is the identity on vectors, more or less, right? And so the reason, okay, so let me see, all right? So the reason why you can replace this, right, with this, of course, is that this is applying, so going from here to here is really just the rigidity condition on the retraction. It's like on the original space R bar, right? And yeah, and so that's how you get the rigidity condition. It's like on the induced map, it's like is implicitly in terms of the rigidity condition of the original retraction. Okay, and this is true for all. It's like elements of this, and you also use the property of the horizontal lift, right? All right, so so again, it's like one has to be a little bit careful. It's like so let me sort of just make the remark that right, yeah. So so in general, it's like one has to be a bit careful. It's like to make sure that more or less it's like these horizontal distributions, it's like sort of transform in the right way. It's like along each fiber, right? So in general, it's like the horizontal lift you define, it's like may not have the property that you satisfy this condition that going around this diagram, it's like it's independent of that choice. Okay, it's much easier to satisfy this property. So let me sort of maybe make the remark that when you have an equivalence relationship, which is defined in the following way, right? So if the equivalence relationship on M bar, right, sort of comes from a Lie group action on M bar, okay, then it is easier sort of to construct a horizontal distribution with the appropriate invariance property. Okay, so that's kind of a vague statement. Let me sort of try to at least explain in words what I mean by that. So imagine, for example, you have a vector space, say Rn, and imagine you have some sort of group action. Imagine, say, the space of rotation matrices acting on Rn. Okay, if you take Rn and you want to, you could, for example, consider an equivalence relationship on Rn. It's like where you say that 2 points in Rn are related to each other if they are related by some rotation matrix, right? So if you can take one point in Rn and rotate it to another point in Rn, it's like true an appropriate application of a rotation matrix, then we might be interested in an equivalence relationship which says these 2 points are equivalent. Okay, and if you're in that situation, it's like then this fiber, it's like becomes defined in terms of a group orbit. Okay, what that means then is that you can get any point on the fiber to any other point on the fiber. It's like true and appropriate, say, rotation. It's like in the example which we had. All right, and the advantage of having sort of the equivalence relationship be defined, it's like in terms of this Lie group action, is that since it's an action which lives on this space, you can then basically pick a horizontal distribution in one space and then sort of move that around, it's like along the fiber through this group action. Okay, and in so doing, it's like you have then a choice of horizontal subspaces, which plays nicely in some sense. Okay, and so that has benefits. It's like when you're then trying to satisfy this condition, it's like which I had sort of erased. It's like what I refer to as the start equation, which guarantees that the retraction you have then is well defined. Okay, so there's a deeper discussion of this issue. It's like in the textbook, but again, the high-level picture is that if this equivalence relationship, if these fibers, which are the preimages under the projection map, right, can be thought of as group orbits, where you take a point, it's like an M bar, it's like, say you look at the space of rotations acting on that point, it's like and all possible rotations at that point then gives you this fiber, right? Then there becomes a very systematic way to take the choice of a particular horizontal space at a particular point and then move it everywhere and transform it in such a way that it becomes easier to satisfy this condition on the retraction on the full space and having it induce a well-defined retraction on the quotient space. Okay, so let me just stop here for now, and we'll continue talking about how you can use these retractions then to define line search algorithms.